everybody. I wanted to start out today by going over a puzzle that I left you with last time. And then after I do that, I'm going to basically just walk through many of the proofs that I gave you guys as homework assignments last time. I'm going to focus on the ones that I think are most useful and most important. I will not be doing all of them, but I will be doing several of them, including some of the ones that are more difficult. All right, so here's the puzzle that I left you with last time. I showed you this argument. If God does not exist, it is not the case that if I pray, then God answers my prayer. I do not pray, therefore God exists. And I showed you last time that if you symbolize this argument in a particular way, then you can actually prove the conclusion from the premises. And I asked you what went wrong. What went wrong is the way that I symbolized the first premise. So here on the screen, I have written down the correct way of symbolizing the first premise of this argument. All right, as I mentioned last time, in ordinary English, when someone denies a conditional, when someone says that a conditional is not true, what they usually mean is that if the antecedent is true, then the consequent is false, right? So when I say it is not the case that if P then Q, that means if P then not Q. Pretty much all of the time in ordinary English. We'll actually see a little bit why that is when I do one of the proofs that I gave you guys for homework later on in this video. All right, so let's get started on the homework. Here we go. One thing that I asked you to prove is that not parentheses P or Q is logically equivalent to not P and not Q. All right, and to prove that, you just prove that the statement on the left entails the statement on the right. And then you prove that the statement on the right entails the statement on the left. And here's how you do that. So this is the first half of the proof. I have one premise. The premise is on line 1. And I want to talk you through how I want to prove this. I'm trying to prove not P and not Q. My conclusion is a conjunction. And so probably the easiest way to prove it is to use my and introduction rule. And to use my and introduction rule to get my conclusion, I'm going to have to prove not P, and I'm going to have to prove not Q. And those two statements are both negations, so I'm probably going to have to use my negation introduction rule. All right, now, to prove not P, using my negation introduction rule, I just start out assuming that P, and then I use that supposition to prove a contradiction. All right, so on statement number 2, line number 2 of this proof, I'm going to suppose P. And I'm just going to try to prove a contradiction. Okay, so on line 3, I write down P or Q. That comes from line 2. It's my or introduction rule. And then line 3 and line 1 contradict each other, right? So on line 4, I write down the contradiction. P or Q and not P or Q. That comes from line 3 and from line 1. That's my and introduction rule. And that's a contradiction. So my supposition is false. Line 5 says not P. And that comes from lines 2 through 4 from my not introduction rule. All right. Now I'm just going to do the exact same thing to prove not Q. So on line 6, I suppose Q, and I try to prove a contradiction. Line 7, I get P or Q. That comes from line 6. That's my or introduction rule. Line 8, I get P or Q and not P or Q. That comes from line 7 and line 1 from my and introduction rule. And it's a contradiction. So my supposition was false. And on line 9, I get not Q. And then lines 5 and 9 give me not P and not Q. which is exactly the thing that I was trying to prove. All right, let's do the next one. This time we're going to use not P and not Q as our premise, and we're going to try to prove not parentheses P or Q. All right, so I've written down my premise on line 1. The statement that I'm trying to prove is a negation, so I'm probably going to use negation introduction to prove it. And to use negation introduction, I start out by supposing the opposite of what I want to prove. So on line 2, I suppose P or Q. All right. Well, from line 1, I get not P. That comes from line 1 by and elimination. And then I can combine lines 2 and 3 to get Q using my or elimination rule. So line 4 says Q. But line 5, not Q. That comes from line 1 by and elimination. And lines 4 and line 5 contradict each other. So line 6 says Q and not Q. That comes from line 4 and line 5 by and introduction. And it's a contradiction. So my supposition must be false. So line 7 says not parentheses P or Q. And that comes from line 2 through line 6 using my not introduction rule. All right, so that's an example of how to prove the two statements are logically equivalent. I assume the first one to prove the second, then I assume the second one to prove the first. All right, here's another problem I gave you. Prove that not P or not Q is logically equivalent to not parentheses P and Q. All right, we're going to do the same thing. We're going to use one of these statements as a premise and use it to prove the other one. And then we're going to use the other one as a premise and use it to prove the first one. All right. So here's half of this proof. My premise says not P or not Q. And the conclusion I'm trying to prove is a negation. So as always, I'm just going to start out assuming the opposite of the negation. I'm going to assume P and Q. All right, that's line 2. Line 2 is the supposition P and Q. All right, now I'm just going to use my and elimination rule twice. That gives me P and it gives me Q. And you can see that, line 3 plus line 1 should be enough for me to prove not Q. All I have to do is find a way to turn line 3 into not P instead of P. All right, not P is a negation. So on line 5, I'm just going to assume the opposite of that. I'm going to assume not P. And now you can see immediately line 3 and line 5 contradict each other. So line 6 says P and not P. That comes from 3 and 5 by and introduction. That statement is a contradiction. So the supposition on line 5 must be false. So line 7 says not P. That comes from lines 5 through 6 by not introduction. And line 7 I can combine with line 1. I can use my or elimination rule to get not Q. So that's what line 8 says. And now line 8 contradicts line 4. So line 9 says Q and not Q. That's my and introduction rule. That statement is a contradiction. So my original supposition on line 2 must be false. So it is not the case that P and Q. All right, that comes from 2 through 9 by not introduction. Okay, that one was just a little bit longer, but still, not too bad. All right, so let's look at the second half of this. This one will be a little bit longer, but again, it won't be too bad. So my premise is it's not the case that P and Q. All right, and now I'm trying to prove a disjunction. And, one way to do that is to use my or introduction rule. But in order to do that, I would have to prove not P, and then I would have to prove not Q, and I just don't think that premise 1 is going to let me do that. So instead, I am going to use my not introduction rule again. All right, this is just a totally normal strategy in logic. If you don't see an obvious way to prove something, prove it with not introduction. Just assume the opposite of what you're trying to prove and get a contradiction. All right, so on line 2, I'm going to assume the opposite of what I want. I'm going to assume it is not the case that not P or not Q. That's line 2. That is a supposition. And now I'm just going to recreate a proof that I did a minute ago, right? I've already proven that if you have not and then a disjunction, that what you get is not the first thing and not the second thing. All right, and so I'm going to recreate the first several steps of that proof as a way of sort of getting rid of the not that's on the outside of the parentheses on line 2, right? So on line 3, I assume not P, the first piece of that disjunction, just like I did in the problem earlier. And on line 4, that gives me not P or not Q by or introduction. And now line 4 contradicts line 2. So on line 5, I write down the contradiction. That comes from 2 and 4 by and introduction. Since that's a contradiction, the supposition on line 3 is false. So line 4 says not P. And line 5, that's equivalent to P by my not elimination rule. All right, so I'm going to continue the same way I did that proof before. I'm going to assume not Q. And now on line 7, that gives me not P or not Q. Line 7 contradicts line 2. So on line 8, I write down the contradiction. Sorry, the parentheses next to line 8 are wrong. That should say line 7 and line 2 and introduction. But that's a contradiction. That means the supposition on line 6 is false. And so line 9 says not Q, not the supposition on line 6. That comes from line 6 through 8 by not introduction. And line 10, that just means Q. Okay, that comes from line 9 by not elimination. Now look at line 5 and line 10. That gives me P and Q, my and introduction rule. And now line 11 contradicts line 1. So on line 12, I write down the contradiction from line 11 and line 1 by and introduction. And that means the supposition that I made on line 2 is false. So on line 3, I write down not, parentheses, not P or not Q. That comes from line 2 through line 12 by not introduction. And then I just use my not elimination rule. All right, good. So the next problem has an easy half and a difficult half. So now we're going to prove that P and not Q is logically equivalent to the negation of P arrow Q. All right. As before, we're going to, use one of these premises, use one of these statements as a premise to prove the other. And then we're just going to do the reverse. All right. This logical equivalence that we're about to prove explains why, in ordinary English, when people say it's not the case that if P then Q, they do not intend to negate the entire conditional. They just mean to negate the consequent. All right, so just think about this for a second. If I say it is not the case that if I die, my girlfriend will be happy, all right, I do not mean that I am dying and my girlfriend is unhappy. What I mean is that if I die, then she'll be unhappy, right? So keep that in mind. If you put a not sign in front of an entire conditional, logically that's equivalent to saying P and not Q, all right? Which is not what we mean in ordinary English when we say that we don't accept a particular conditional. All right, so we're going to do the easy half of this proof first. Here it is. Our premise says P and not Q. And now we're trying to prove the negation of a conditional. So on line 2, we just suppose the conditional is true, and we're going to try to prove a contradiction. All right, well, from line 1, we get P, just from and elimination. And then by arrow elimination from lines 2 and 3, we get Q on line 4. But we have not Q from line 1 by not elimination, and so now we have a contradiction. And on line 6, we write Q and not Q. That comes from lines 4 and 5 by and introduction. That is a contradiction. And so the supposition on line 2 is false, and our conclusion is it is not the case that P arrow Q. All right, now, as I said, that half of the proof is easy. The second half of the proof is much harder, and I'm going to do it for you in 2 different ways. The first way I'm going to do it, I think, is conceptually easier to understand. It makes a little bit more sense, I think, for most students who are doing this for the first time. The second way I do it is going to be a little bit faster, but it's also a little bit more confusing. All right, so here's the first way. You can see this is quite a lot longer. So, my premise is it is not the case that P arrow Q. And what I want to prove is P and not Q. So I'm just going to start out supposing that's false. So I get not, parentheses, P and not Q. Well, I've already done a proof that tells me what to do whenever I have not followed by a conjunction. And so what I'm going to do is I'm just going to basically copy that proof so that I end up proving not P or Q, right? So if you look ahead to line 16, that's what I get on line 16. I get not P or Q. And, all I'm doing to get there is I'm copying the proof that I did several problems ago that tells me how to get rid of a not that is outside of a conjunction. All right, so on line 3, I'm assuming that line 16, which I'm trying to prove, is false. So it says not, parentheses, not P or Q. I suppose not P. On line 5, that gives me not P or Q by or introduction. And now line 5 contradicts line 3. So on line 6, I write down the contradiction. That contradiction proves that the supposition on line 4 is false. So line 7 says not P. And on line 8, that's just P by not elimination. All right, then I'm going to suppose that Q. That gives me not P or Q by or introduction. Line 10 now contradicts line 3. So on 11, I write down the contradiction. That contradiction proves that the supposition on line 9 is false. So on line 12, I get not Q. So now on line 13, I have P and not Q. And that contradicts line 2. So on line 14, I write down the contradiction. That proves the supposition on 2 is false. So on 15, that proves the supposition on line 3 is false. So on line 15, I write down not, parentheses, not P or Q. 16, by not elimination, I get not P or Q. All right, now, all I've done so far is I've written down line 2 differently. Okay, it took me 15 lines now to turn line 2 into a statement that's easier to work with. All right, so line 16 says not P or Q. All right, and now I need to find a way of getting a contradiction out of that. Somehow line 16 has to contradict line 1. All right, so suppose P were true. And then suppose that not P were true. I know that this sounds super weird, but this will make sense in a second. On line 19, I get P and not P. That proves the supposition on line 18 is false. So on 20, I get not P. All right, so here's what I did. I supposed that P, and the reason I'm doing this is I'm trying to prove the Q. I'm trying to get the conditional P arrow Q because that would contradict line 1. The only way to get that conditional is by supposing P and using it to prove Q. So that's what I'm doing here. On 17, I suppose that P. And now I look at line 16 and I realize that if instead of P I had not P, I could use that combined with line 16 to prove Q. Okay, so 17, I suppose that P. And I use that to prove not P. Okay, so line 18 says not P, the opposite of what I'm trying to prove. Line 19 is the contradiction, so on line 20 I get not P. You combine 20 with line 16, and on 21 that gives you Q. So line 22 says P arrow Q, and that finally contradicts line 1. So on line 23 I get a contradiction. All right. That means the supposition all the way back on line 2 is false. So I get not P and not Q. And now by not elimination, finally on line 25, I get P and not Q. All right. That is the long way to do this, but it's also the conceptually easier to understand way of doing this. Here's a slightly trickier proof, but it's a little bit faster. So again, my premise says not P arrow Q. All right. And the way I'm going to do it this time is I'm going to start out trying to prove P, and then I'm going to prove not Q, and then I'm going to use my AND introduction rule to get P and not Q. Okay, so I'm going to prove P first, and in order to do that, I'm just going to suppose the opposite of P. I'm going to suppose not P. All right, and now somehow I have to get a contradiction. And the only way I can really get a contradiction is to prove P arrow Q. So on line 3, I'm going to suppose that P. And now in order to get P arrow Q, I have to prove Q. So I'm going to suppose not Q. All right. And now I have a contradiction on line 5. Lines 2 and 3 contradict each other. So I write down the contradiction on line 5, and that proves my supposition on line 4 was false. So on line 6, I get not Q. And then on line 7, by not elimination, I get Q. So I assumed, P on line 3, and I proved Q on line 7. So that means on line 8, I've proven P arrow Q by my arrow introduction rule. And line 8 contradicts line 1. So on line 9, I write down the contradiction. That proves that the supposition on line 2 is false. So line 10 says not P. That's from 2 through 9 by my not introduction rule. And then on 11, by my not elimination rule, I get P. All right, so that's halfway done. Now I have to prove not Q. And in order to do that, I'm just going to suppose that Q, and I'm going to find a contradiction. So line 12, I suppose that Q. And now again, to get a contradiction, I really need to prove P arrow Q. So on line 13, I'm going to suppose that P, and in order to get my conditional, I have to prove the Q now. So on line 14, I'm going to suppose that not Q. And on line 15, I get a contradiction because line 12 and line 14 contradict each other. So Q and not Q. On line 16, that means the supposition, on 14 was false, so I get not Q. And then on line 17, by not elimination, I finally get Q. So on line 13, I supposed P. On line 17, I proved Q. So that means on line 18, I have P arrow Q by my arrow introduction rule. And line 18 contradicts line 1. So I write down the contradiction on line 19, which proves that the supposition on line 12 was false. So on line 20, I get not Q. And now 11 says P, 20 says not Q. So on line 21, with my AND introduction rule, I get P and not Q. All right, now you can see that proof is faster. It's about 4 lines faster. But it's a very weird proof, right? Line 2, 3, and 4, I make 3 suppositions in a row, and the first 2 suppositions I make contradict each other, right? Line 12, 13, and 14, again, I make 3 suppositions in a row, and the first supposition and the third supposition contradict each other, all right? So this is a way of proving this that sometimes people find a little bit confusing. but you can see it's a faster way to do it. All right. Here's the next problem. We are going to prove that P arrow Q is logically equivalent to not P or Q. All right. So here's the first half of the proof. My premise is P arrow Q. And now I'm just going to suppose the conclusion is false, as I so often do. So line 2, the supposition is, it is not the case that not P or Q. Okay? And we already did a proof that shows you, how to handle a situation where you have a not sign on the outside of a disjunction. So we're just going to start out following that proof. On line 3, we're going to suppose not P. On line 4, that gives us not P or Q by or introduction. And you can see that line 4 contradicts line 2. So on line 5, we write down the contradiction. That proves that the supposition on line 3 is false. So on line 6, we have not P. That's lines 3 through 5 because of our not introduction rule. All right. On line 7, we get P by eliminating the knots on line 6. There's a typo there. The parentheses should say line 6, not elimination. And now you can see that if you combine line 7 with line 1, you get Q. Right? So that comes from line 1 and line 7 by arrow elimination. And then from line 8, we get not P or Q, just using our or introduction rule. And line 9 contradicts line 2. So we write down the contradiction on line 10. That proves that the supposition on line 2 was false. So on line 11, we write down it is not the case that it is not the case that not P or Q. That comes from line 2 through line 10 by not introduction. And then on line 12, we just eliminate the double negation. And that's our conclusion, not P or Q. All right. Here's the opposite direction of that proof. It's much, much, much easier. All right. So our premise says not P or Q. We're trying to prove a conditional, P arrow Q. And so we're going to use our arrow introduction rule. Starting on line 2, we're going to suppose that P. All right. And now you can see that if we had not P instead, that we would be able to use that with line 1 to prove the Q. So we want to prove not P now. And we're going to prove that by assuming the opposite. We're just going to assume not P. And then on 4, we get a contradiction, right? Line 3 contradicts line 2. So we get a contradiction on line 5. We've determined that the supposition on line 3 was false, so we write down not P. That's lines 3 through 4 by not introduction. And then line 5 plus line 1 gives us Q by or elimination. All right, so on line 2, we suppose the P. On line 6, we've proven the Q. And now on line 7, we get P arrow Q. There's another typo here that should not be a premise. P arrow Q is something that we proved with lines 2 through 6 by arrow introduction. All right. Now, there's another problem I gave you that it's very important to see the answer to. This one had 3 premises. The premises were P arrow R, Q arrow R, and P or Q. And the conclusion is R. All right. And now this is a really interesting argument. This is an argument that's going to be important later on in the course. It's going to keep coming up again and again and again. So here's how you prove it. All right. We have 3 premises. We're trying to prove that R. So we're going to start out supposing that R is not true. We're going to suppose not R. All right. And now I've already shown you how with statement 1 and statement 4, you can prove not P. Okay, I showed you that on a previous video. So we're just going to repeat that proof. We're going to suppose that P. Then from line 5 and line 1, we get R by our arrow elimination rule. And now line 6 contradicts line 4. So on line 7, we write down the contradiction. And that proves that the supposition on line 5 is false. So on line 8, we get not P. That's 5 through 7 by not introduction. And now if you look at line 8 and line 3, it proves Q. All right, by or elimination. So line 9 says Q. And now if you look at line 9 and line 2, that proves R by our arrow elimination rule. And line 10 contradicts line 4. Okay, so on 11, we write down the contradiction using our and introduction rule. That contradiction proves that the supposition on line 4 is false. And so on line 12, we get not R. That comes from 4 through 11 using our not introduction rule. And then we just use not elimination to prove that R. All right, so that's a pretty easy proof. Here's what's really fun about this proof, though. This argument turns out to be interchangeable with our OR elimination rule. All right. If we did not have the OR elimination rule, we could have used this argument instead. And we would be able to prove all of the exact same things. All right. And so right now I'm going to show you how to prove that. As I said, this argument's going to be important over and over again. So this is important to understand. All right. Here's what we're going to do. We're going to prove that the OR introduction rule, sorry, that's a mistake. We're going to prove that the OR elimination rule is interchangeable with P arrow R, Q arrow R, P or Q proves R. And here's how we're going to do this. We're going to assume that the OR elimination rule does not exist. We're going to assume that we don't have that rule. And we're going to prove that P or Q and not P entail Q by using the argument that I just gave you instead. So here's how we do that. We have two premises. The first premise says P or Q. The second premise says not P. And, you know, what we want to prove is Q. That's what we really want to prove. And we have to find a way to do that using the argument I already gave you. Well, the argument I already gave you says that if we had P arrow Q and if we had Q arrow Q, then we could combine it with premise 1 to prove that Q. So we need to prove a couple of conditionals. The first conditional we need to prove is Q arrow Q. So on line 3, we're going to suppose that Q. And now we have to prove that Q. But you can already see Q is written down on line 3. So there it is, right? On line 4, we get Q arrow Q. That just comes from line 3 by arrow introduction. And now we want to prove P arrow Q. So on line 5, we suppose P. We're trying to prove Q now, so we're going to suppose not Q. And now you can see that line 5 actually contradicts line 2. So on line 7, we write down the contradiction. On line 8, that proves that the supposition on line 6 was false. So on line 8, we get not Q. And then on line 9, that just gives us Q from not elimination. So we supposed P on line 5, we proved Q on line 9, and so on line 10, we have P arrow Q by our arrow introduction rule. And now you can see we have P or Q, we have P arrow Q on line 10, we have Q arrow Q on line 4, and that gives us Q. All right, and I've written down in the parentheses the inference rule that we could use to prove that, right? So this is what's interesting about this argument. The inference rule that I've used on line 11 is an inference rule that we can use to prove our OR introduction rule. And I've already shown you how we can use our OR introduction rule to prove this inference rule, right? So those two inference rules turn out to say basically the same thing as each other. If we keep all of our other rules the same, those two rules can actually, they can be substituted. Anything that we can prove with one of them, we can also prove with the other. All right, so that's basically all I wanted to cover today. There are a lot of mistakes on these slides. I'm sorry about that. I will, when I have time, go back through and try to fix all of that. And you know, after I fixed it, I'll try to send you some revisions. But yeah, we'll do some more of this in my next video and start getting ready to introduce a couple of the next topics that we're going to be covering.